Okay, I think it's time to start. And sorry for the delay, but well, we are in Hawaii, so. And right now we have some internet connections, technical issues, so this will be just in person, but hopefully we'll fix it for the later session. And then we have the presentations online, so hopefully people that wanted to attend on Zoom will be able to see those online. So welcome everyone to our in-person meeting. It has been a while, so we are very happy to see you all here. And please use this workshop to discuss all geospace science problems and research directions in final preparations for the heliophysics decadal survey. And before we start, just brief announcements here in these slides today. So please follow the policies for GEM. We know that COVID is still around, so please, if you would like to wear a mask, keep social distancing, respect each other choices. And also we have a anti-harassment policies that you can find on the GEM wiki main page. And I hopefully we won't have any problems, but in case anybody sees something that is wrong and would like to report, there is also a link there where you can go and report even anonymously, or please come and talk to anybody on the steering committee. So we have made a lot of changes since we had an in-person meeting several years ago. We pledged to support diversity, equity, and inclusion. So we have formed DI subcommittee who worked really hard to organize several special events for this GEM. We also organize DEI happy hours throughout the year, and I encourage you to join those. They are together with CEDAR sometime. We have initiated a Sam Bingham Community Care Initiative. And for this special GEM workshop, we have organized several events. So one is the training session this afternoon, Speaking Up. So you probably saw this flyer next to the registration. So we have invited some power play and inclusion companies, and they have prepared a special training session for us that will be interactive and hopefully interesting. So please join it. We have also on Wednesday invited speakers to talk about relationships with indigenous populations, and we will have a social hour and Sam Bingham Memorial on Friday. So we also continue our program, GEMI mentoring program, and this year we had 33 mentors and 34 mentees. Obviously, we need more mentors, and thankfully one of the mentors is mentoring 2 people, so we are okay for this year, but please join. I'm sure the students will greatly appreciate sharing with them your experience and also advice for career development. And also we have started in the GEM, so we just published the gemstone. You can find it on the GEM wiki. And we have in it a lot of information about the activities that were throughout the year, both from focus groups and liaisons. And you may also read a memoriam for Josh Sisko, who we lost in April. And this was the founder of GEM and a great colleague and friend to many of us. So here are the steering committee voting member. This is the core of the GEM steering committee, and they have been working really hard throughout the year to organize this workshop. And also we have an opening for 4 new steering committee members to replace Alison, Alex, Steve, and myself. My term is ending, so we will have a new vice chair. So this application process is still open and we can still apply until Wednesday. So please, if you have any questions, talk to any steering committee members and they will explain what these roles are about. But many thanks for the outstanding service to the GEM community of all steering committee members. We also have right now 11 active GEM focus group. There will be one on the top, the 3D ionospheric group that will be ending this year. We have 3 new here on the bottom that are starting this year. And we will have a call for new focus groups in the fall. So again, please consider submitting a proposal. That is how GEM is working through the organizations of the focus groups. And we have a new NSF GEM director. Please stand up. So you all know Chailin. She doesn't need an introduction, but we are really happy to have her as our new GEM director. And we also have liaisons that connect us with the other organizations, both local in the US or international. And again, you may read about their activities in our newsletter. And finally, some practical information. So we have more than 300 people registered, which is great. GEM is growing, more than 100 students. And we also give family care grants. We gave 7, so there is 1 more available. If somebody is in need, please contact us. We received more than 190 posters. And the posters will be, if they are not in display for Tuesday, soon. For Thursday, we have a little change. The Thursday posters will be actually displayed on Thursday morning because we will need the room for the banquet. Also, I would like to mention that the hotel was very willing to accommodate us. So they transformed one of their bathrooms to a gender neutral bathroom that is here on the 6th floor. And of course, there will be opportunities for communication during and after the workshop, as we did in previous years, through the vgem.org and through the Slack workspace. If you haven't joined, so please join those. Thank you. And again, sorry for the delay. And I would like to invite the student moderators to introduce our first speaker, Ian Zhu and Shantung Wang. I guess we go to is this the one?
Yes, this is my script. Hi, it is my honor to introduce Dr. John Dorelli. Today, Dr. Giovanni will give a tutorial on the GSM. Dr. Dorelli received his undergraduate degree from the Purdue University in 1993. He received his PhD in physics, working with his advisor, Jack Scudder from the University of Iowa in 1999, after which he worked for several years as a postdoc at the Los Alamos National Laboratory. Dr. Dorelli was a member of the research faculty of the Space Science Center at the University of New Hampshire for 6 years, before coming to the NASA GSFC as a civil servant in 2009. Let's give Dr. Dorelli a warm welcome.
So obviously that's not me, and the slide is a little bit out of order, but I thought before I dive into my talk, I'd mentioned that it is Juneteenth, which is a federal holiday now, today, observed. So I thought since there are a lot of model developers in the room, I'd say a few words about the history of computing at NASA. So many of the models that I'll be mentioning today were written in Fortran. And I know from personal and often painful experience, sometimes in Fortran 77, no indented code. I'm not going to name or shame anybody, but you know who you are. So there's a really great scene in the movie Hidden Figures where I think it's at Langley. I forget where NASA has this IBM mainframe that's kind of sitting there collecting dust because nobody knows how to use the thing. And Dorothy Vaughan went to the library and picked out a Fortran book. And in the movie, it looked a lot like the Fortran book that was on my advisor's shelf. And she not only taught herself how to program this machine in Fortran, but she taught her colleagues so that they could do useful things with this machine. So I thought it fitting to mention that. We're in a kind of new age now with Python and cloud computing, and we're kind of spoiled by the access that we have to these complex algorithms and massive amounts of computing power. But just imagine trying to program that thing on punch cards. So I think we've come a long way, and in a lot of ways, we're walking in their footsteps. So I'd also like to say a few things about George. I didn't know George very well. I met him a few times. I chatted with him at meetings. And I think like many of you, I always came out of those conversations very inspired. George had this way of writing scientific prose, which was kind of poetic, I thought. And I had first encountered this in a review paper that I read as a graduate student on MHD. And if anyone who can make MHD poetic and exciting and grand, really you can inspire anybody, right? So when I found out that George retired and opened up a bookshop in Maine, I put that on my to-do list to visit that because I live in Massachusetts now, but I never got a chance to do that, and it's now temporarily closed. So I went online and I found this great article by John Doucette, and this quote I think perfectly captures not only George's writing style but his approach to science. And so he had half of the bookshop was science and technical stuff, and the other half was the humanities section. And George thought you needed both of these things, not just sort of all the facts and things that you were learning about the magnetosphere, but why it was important. And so you always felt you were part of some grand story and engaged in an intellectual endeavor of the highest order, like fundamental physics or astronomy or cosmology. And I always appreciated that. And I think that energy infused GEM at the very beginning, and it continues to this day, and we benefit from it. So I just wanted to thank George. So I was invited here to talk about how magnetic reconnection, kinetic scale reconnection, impacts the global scale. And so you might think that's a contradiction in terms because reconnection is a microphysical process. It occurs at a very localized region. What possible impact does it have on the global scale? So I think from the earliest days, oh, full screen, go ahead. So from the earliest days of GEM, I think the way people viewed this was if you could just find some parameterization of things like resistivity, and you just get that thing right, the transport coefficients, then MHD could really kind of mimic the collisionless process. So I'd like to take a slightly different approach and make the argument that there are basic structural problems with the MHD equations that have impact on just the basic structure and dynamics of planetary magnetospheres. You can't just get those by parameterizing some microphysics. So the earliest ambition of GEM was to, we'd have these theory campaigns, and each of these campaigns would treat a different section of the magnetosphere. And over time, you would develop these local models kind of independently, like modules, and they would emerge into this GGCM, where all the pieces were put together. And I think it was a little bit ambitious in the 90s to think that this was going to happen in 2 to 3 years. So several decades later, though, I think we basically realized this ambition, and we have models that have been developed over years at different institutions, and they've been coupled together bring a bunch of talented software engineers into the game and you can do amazing things. And what you'll notice though, is that at the center of this, kind of gluing everything together are MHD models. And I think the reason for that is very simple. There were lots of big advances in computational fluid dynamics, finite volume schemes. They're very efficient. You can solve them very efficiently on computers at the time, and even in the 90s and even in the 80s. And they could do really magical things, like you could capture shocks and discontinuities. You didn't have to do anything special to do that and get them basically in the right locations. You could get complex 3D magnetic topologies. You even get, with high resolution now, you can get mesoscale dynamics like flux transfer events, BDFs. The global field aligned current systems are basically right. And then you can easily couple them. I won't say easily, it took a long time, but you can couple them to different sources of plasma, like the polar wind, their plasmasphere models, the ring current, ionosphere, thermosphere. So these are pretty sophisticated. So what I'd like to try to point out is some of the ways I think where this MHD spine approach maybe go wrong. Maybe saying go wrong is a little bit too negative. So there's some gaps I think that could be filled. So, and I think there are three basic areas here. The magnetosheath, we're all familiar with how MHD doesn't have the foreshock waves. The bow shock rippling, fast flows in the magnetosheath, turbulence, all that stuff impacts dayside magnetopause reconnection, and we all know that. It's kind of obvious. But you can really, global hybrid codes cover this nicely. It's not clear yet where that story is going to lead in terms of the full coupled system. What I'd like to do is focus on some less obvious places where MHD really gets the global scale wrong. And I'll focus on 4 basic areas. So we've got dispersive Alfvén waves. And we all know how important those are for driving field aligned currents in the aurora during active times. But I'd like to emphasize how this connects directly to magnetic reconnection physics in the magnetosphere. Parallel particle transport. Well, you can't have dispersive Alfvén waves or field aligned currents without the particles that carry those things. Those things have an impact on the ionosphere, significant impact on things like ionospheric conductances. Those things feed back. Oh, thank you so much. Those things feed back onto the magnetosphere. And then electron finite Larmor radius effects. So this goes to the question of, can we parameterize things like resistivity in global codes? And I think MMS has taught us a lot of unexpected things about how one might incorporate FLR effects into a global model. And then I'll talk about how it doesn't actually work. About how those first 3 effects impact MI coupling. And I think MI coupling is one of the big gaps in global modeling. It's not clear how all of the kinetic physics in the magnetosphere couples to the magnetosphere, in particular from a modeling perspective. It's just a very difficult problem to address. And so for that reason, it hasn't really advanced as far as these other coupling approaches. All right, so first, dispersive Alfvén waves. So the way I like to think about this comes from what I'll call the standard model of magnetic reconnection. And I think we all know this from the GEM reconnection challenge, the main result here. Oh, thank you. I keep having people come up and give me things, which is great. Oh, awesome. Thank you, man. So we all know from the GEM reconnection challenge, the big result there was that reconnection develops this multi-scale structure. So there's an ion scale structure and there's an electron scale structure. These things are very widely separated. And so the reason for that is the ions become unmagnetized, but the electrons stay magnetized. So as the ions become unmagnetized, the electrons keep flowing into the EDR. And some magic happens, and the electron dissipation region becomes very localized. And that results in fast reconnection. That was the big result of the GEM reconnection challenge. And all you need to get that is the Hall effect. So there's been some, a discussion that's gone on for decades about what is the relationship between the dispersive waves and this localization. And I don't think we have the answer to that yet. Although Yixin Liu has a paper out recently that is trying to explain this effect, this localization effect. It may not have as much to do with dispersive waves as we once thought. But regardless of what the relationship is to the localization, the dispersive waves might be very important for the global structure of the magnetosphere. And this was first posited by Mike Shea in 2011. So, you know, in a PIC simulation or in any Hall MHD simulation, you have this out of plane magnetic field structure, and it carries field aligned currents. And you can think of it as a kinetic Alfvén wave that's propagating obliquely to the magnetic field. But it has a parallel component of pointing flux. And Mike Shea wondered, does that actually propagate all the way to the ionosphere and make the aurora? That's kind of an obvious thing to wonder. I think a few years later, computers were big enough where we could actually start to think about doing global Hall MHD simulations at very high resolution. And you need high resolution to really kind of get this physics right. And that's very challenging with Hall MHD. It just takes a lot of computing time. And the reason being because these dispersive Alfvén waves propagate very fast. And so you have a stability condition for these codes. But what you find is that indeed in Ganymede's magnetosphere, Ganymede's a very small magnetosphere, but it's still, you know, maybe a factor of 10 larger than the ion inertial length. So it's small, but you can consider it to be large in some sense. But you see that this quadrupole pattern actually propagates all the way to the surface of the moon, and solves a puzzle that people had been wondering about from Hubble observations of the aurora about the distribution of the aurora at Ganymede. So MHD simulations really don't get this field aligned current pattern right at all. They get it completely wrong. If you put the Hall term in there, suddenly you get this field aligned current pattern that connects directly to the reconnection site. So that's very interesting. One might ask, well, how does this scale up to Earth? And that right now is a difficult question to answer because we don't have the computing power to do this yet. So the other thing you get from the dispersive waves or from this out of plane magnetic field pattern is less well known. And I'll call this the Hall generated ion jet. Well, if you look at the Hall current and you just take the J cross B force in the magnetic field, these reconnecting field lines, you get a J cross B force that's out of the plane. And that accelerates ions to the Alfvén speed out of the plane. And so you get this anytime you have reconnection and you have this Hall effect decoupling the ions and the electrons. So then you might ask, well, if you have reconnection going on all the time in the magnetotail, what impact does this have on the convection pattern? And so, you know, we looked at this with our Ganymede simulations, and pretty soon we had other groups looking at the same thing. So you can think of this as sort of an unofficial GEM challenge, where we looked at the same magnetosphere with different types of models. You know, so we have Hall MHD, full PIC, and this two fluid 10 moment model. And they all see the same convection pattern, which is completely different than the Dungy pattern that people thought you would see at Ganymede from MHD simulations. So that's also very interesting. But then the question again is, how does this scale up to the real Earth? Okay, so we can't really do a full scale Earth, but what we can do is we can play tricks, which is what everybody does when they do this kind of kinetic modeling. As you say, well, let's just artificially inflate the kinetic scale, you know, to some fraction of, you know, Earth radius or something, but keep everything else the same. So it's like you're self-similarly scaling down the magnetosphere, but the bow shock and the magnetopause are kind of in the right places relative to each other. So you can do what we'll call mini Earth, and this was done by Chris Bard just a couple of years ago. Last year, actually, this appeared. And what you find is very interesting. You see the same kind of convection pattern where you get this ion jet across the tail. Ions moving duskward, electrons are moving dawnward, which is very familiar from anyone who does ring current modeling. That's where those things are supposed to go. So what you might expect is that the plasma sheet here should merge kind of seamlessly into the ring current rather than there being this kind of discontinuity between E cross B drift and then suddenly you have a ring current there. And interestingly, you also get that reconnection tends to have a preference for the dawn side rather than the dusk side. So you get these plasmoids that are forming predominantly on the dawn side. There's some debate about what causes that. We see this in both hybrid simulations and Hall simulations. There are a couple possible explanations for that. I think Yixin also has an explanation of that in one of his recent papers as well. But I think what we're seeing, Yixin, is very consistent with your active region idea as applied to a small magnetosphere. Okay, so lest you think that everybody agrees on this stuff, there was a paper, a very interesting paper by Yu Lin. And I think this was probably the first paper that I've seen in literature that pointed out that Hall effects should produce asymmetries. But she saw the opposite. She saw the ions moving in the duskward direction, or I'm sorry, in the dawnward direction. And the explanation she gave was, well, instead of looking at the Hall current, look at the Hall electric field, and then just calculate E cross B drift. And then, of course, you get the drift going the opposite direction. It's not really clear which one of these is the right answer because you can make these cartoon arguments for both. But I think the real answer, and this came a couple of years later with Liu et al., is that some of the ions are magnetized and some of them are not. Some of them are, gradient curvature drifting, and you get FLR effects. And it's only when you sum all of these things together that these things are in competition. One of them wins out. And so that's the answer to this. And I think the answer may be that if you if you do higher resolution simulations, you can resolve some of these ion demagnetization effects and get the drift to go in the right direction. All right, so let's go to the second effect, parallel particle transport. So you can think about the same system, reconnection happening somewhere in the tail, and then look at the structure of the separatrix. And what I just described to you is what you could refer to as the wave picture of the separatrix. But there's also a particle picture of the separatrix that's been around for a long time. And this was first proposed, I think this is the first time this was proposed by Terry-On Sagar in 1991. And the idea was to try to explain these weird, parallel crescent distributions that you saw in the plasma sheet boundary layer. And the explanation involves what's called the velocity filter effect. So if you have this X point somewhere in the tail, and you have some observation point in the plasma sheet boundary layer, then if you say you backwards integrate all these particles, they come from different places in the plasma sheet, and they arrive at different times. So it's the competition between the parallel transport and the E cross B drift toward the Earth that produces these weird distributions. And that's just purely a particle tracing thing, right? So if you have these prescribed electromagnetic fields, then just trace the particles using guiding center drifts, and you can easily pick up these distribution functions. This is interesting because obviously these distribution functions are very highly non-Maxwellian. There's no way you can model them in MHD or Hall MHD for that matter. So you need something more than Hall MHD to get this right. So we have these two pictures, the wave picture and the particle picture. How do we put them together? So here I'll just show some observations. I think it was when I saw this as a graduate student, Terry's paper so beautifully explained these distribution functions. It's just kind of an amazing piece of work, really. You really just get these completely right. The electrons, even with MMS, you can start to see the anisotropies. It's much more difficult to see them in the electrons, but the ions, they really pop out. And so here I have a simple two-dimensional model of the magnetic separatrix region where I just have straight field lines, and I have a polar rain population, the polar cap, and a plasma sheet population. And I use similar parameters to what we saw in this MMS data and just applied this simple one-dimensional time of flight argument and allowing all of the particles to just completely mirror at this low altitude boundary. And at the observation point, you can quickly pick up very qualitatively similar features in just really the simplest model that you can think of involving drift kinetics. So this gives us hope that, that including some of these particle ballistic effects will help us reproduce some of these non-Maxwellian distributions in the plasma sheet boundary layer. So how do we merge these two things? And this is something that is not obvious at all. Really what you need to do is find a model that incorporates electron frozen flux in the perpendicular direction. So you need a perpendicular electron flow that is where the magnetic flux is frozen to that flow, but you have to allow for kinetic parallel transport parallel to the magnetic field. And it turns out that the mathematics was already developed by Russell Colesrid in 1983, and this is what's called collisionless MHD. And this is something that's well used in the plasma fusion community, not so much in our field, mainly because it's just so expensive to do this in a real magnetosphere. But the idea is you just take the regular MHD equations, mass conservation, momentum conservation. You've got Faraday's law here. The Ohm's law comes from integrating this drift kinetic equation. So instead of evolving the pressures and worrying about the closure problem, you solve the drift kinetic equation for transport parallel to the magnetic field. And then you just, once you get the pressures, this gives you those Onsager parallel crescent distributions, calculate the pressures, put them back in here, you have your closure. And then you have an Ohm's law here that's extended by the parallel electric field. And this is just the parallel pressure gradient and the mirror force. Those are the two things that are really shaping the distribution function, the gyrotropic distribution function. So what does this include? This includes the Hall decoupling. It includes dispersive low frequency modes like kinetic Alfvén waves, non-local parallel transport, and including wave particle interactions like Landau and transit time damping. All of that is included in one seamless self-consistent model. Don't need to go full particle for that. So you just need to do the parallel transport right. And in the mathematical formulation is already there. What does it not include? It doesn't include FLR effects, but I'm going to show you in a couple slides how you can easily incorporate those. It doesn't include the collisional interaction with the ionosphere. So you really need a transport model to understand how those precipitating electrons make the aurora. So that's also a missing piece. All right, so let's talk about electron finite Larmor radius effects. All right, so MMS really has illuminated this in a kind of unexpected way. So I think we were expecting to see just Spicer orbits and some obvious signature of in the pressure tensor off diagonal terms. But instead, the first thing that came out were these perpendicular electron crescent distributions. And it was kind of unexpected to a lot of people, but not to Michael Hesse or Li Jian Chen, who actually was the first to go looking for these things. You know, so what makes these? All right, so for a while, people tried to explain these in terms of Spicer-like orbits, right? So you do a particle and cell simulation, you get these particles going from the magnetosheath to the magnetosphere, and they kind of bounce back and forth. You say, yeah, those are kind of meandering Spicer-like orbits. That's what's going on here. Besho has a nice paper explaining this, and that's a true thing. That's a real mechanism for producing crescent distributions. I'm going to skip here, but very quickly, Jan Eggedal realized you can actually explain these things. You don't really need a full kinetic model to explain these. You can also explain these with drift kinetic theory. And the idea is simple. This is going to be a one-slide tutorial on drift kinetics. And I would direct you to these papers, this beautiful paper by Littlejohn in 1981, and then a review paper by Carey and Brizard. It's worth kind of slogging through these things to kind of get your head around it to understand what's going on, but I'll give you the one slide thing. So basically what you do is you take your regular phase space variables and you just rewrite them in a spherical polar coordinate system like this. You've got the position of the particle, you've got the parallel velocity, the magnetic moment, and the gyro phase. If you can find some transformation, just a coordinate transformation to a new set of variables where the Lagrangian doesn't explicitly depend on the gyro phase, then you can immediately write down these guiding center equations. And then from Liouville's theorem, because you're doing this from a Lagrangian point of view, Liouville's theorem applies. You don't have to go through all the gory details of deriving the drift kinetic equation. You can just write it down. And that was what Littlejohn was emphasizing. Just write it down like this. This is just Liouville's theorem in these new variables. And what you notice is that you've lost two of the dimensions. So you no longer have magnetic moment, you no longer have gyro phase. So that dramatically simplifies the kinetic equation that you have to solve. And then here's what Jan Eggedal pointed out, is that what you don't normally see in these treatments is that if you go back to this coordinate system, it means the full non-gyrotropic distribution can be written like this. You can Taylor expand this by just plugging these in and Taylor expand, and you get this gyrotropic distribution, but then you get these FLR corrections. And this is where all the gyrophase dependence lives. And this is also where the crescents live. So you can explain the crescent distributions in this drastically reduced kinetic model. And so if you just take these two equations and calculate the parallel electric field from this one and the perpendicular electron velocity from this one, you end up with this Ohm's law for the perpendicular electric field. It's the Hall term, and then you get these FLR corrections. So I've got the perpendicular gradient of the perpendicular electron pressure, and I have this curvature term that is not bad actually if you have an anisotropy. If you look at the MMS data at one of the EDR events, this was the science paper that I showed you with the crescent distributions, you find that in the region where you're observing these crescents, the perpendicular electric field is really nicely supported by the combination of the Hall term and this perpendicular electron pressure gradient. It works out very nicely. And so that's really all you need to explain the crescents. So that gives us hope for kinetic modeling because it means we don't have to do full pick to get that, at least that FLR effect we can get in a drastically reduced model. Okay, so how does all of this impact MI coupling in these global models? So the usual approach is, we have this simulation and we have some inner boundary that's about 3 RE. It's some sphere here. And what we do is we map parallel currents from this upper boundary here to the ionosphere. And then we use some formula to compute the ionospheric conductances. And that's really, there's a lot of hand waving going on there. That's a very complicated problem. But you have this paper by Robinson that gives you a nice formula involving the energy flux and the mean energy. And you can then compute the ionospheric conductances. Then you use current continuity in the ionosphere and you get an equation, a Poisson equation for the electric field. You map that back up, that gives you the velocity. That's how the ionosphere drives, that's how the ionospheric conductivities drive convection. Very simple. How do we modify this to take into account these 3 effects? So dispersive Alfvén waves, parallel particle transport, FLR effects. It's not really obvious. So how do we do this in the collisionless Hall MHD model? Well, a lot of this may not change very much, right? So we've got parallel current. We can still do the same mapping. We get our conductivities. We use current continuity here. So in a pure Hall MHD model where we have no parallel electric field and no FLR effects, we would just use that to give us the electron velocity in the magnetosphere rather than the ion velocity. But then you have some interesting questions here, right? If you have this collisionless Hall model where you're solving a drift kinetic equation for the parallel transport, how does that actually impact the ionospheric conductivities? And how do we incorporate that full drift kinetic Ohm's law and feed back into the magnetosphere? I don't know the answer to that, but that's a very interesting question that I think we should be pursuing as part of the GEM program. All right, so once you start having electrons precipitate into the ionosphere, now you have to worry about collisional effects. And it turns out that if you do a fully kinetic model of this, you can get interesting things like secondary electrons might be produced in the ionosphere. Those things might bounce back and forth and collisionally interact with the ambient electrons. And it's not clear how that ends up impacting the conductivities, but George Kazanov has argued that has a big effect on the ionospheric conductances. And so somehow you have to include that. Once you go kinetic for the parallel transport, now you have to worry about collisional interactions in the ionosphere. So with that, I'd like to introduce a new project, which we call MARBLE, for Magnetosphere Aurora Reconnection Boundary Layer Explorer. And the goal of this is to include all of those effects I just talked about, dispersive Alfvén waves, parallel particle transport using the collisionless Hall MHD model, and collisional interaction with the ionosphere. And so we're going to build upon an existing 3D finite volume Hall code, solve the electron and ion drift kinetic equations, incorporate the full Hall MHD Ohm's law with the parallel pressure gradient, the mirror force in there, no FLR effects, that's too complicated for now, but we'll start with the parallel electric field. It's going to run on very large clusters of GPUs eventually, and we have now a dedicated cluster at Goddard of 8 A100s that we can just use to run simulations for weeks at a time. And we're going to couple this to a GPU accelerated Fokker-Planck code. And so what we'd like to do is do a little experiment here and see how far we can get by really fully embracing an open science approach to this model development. And by that, I mean, really truly have a collaborative development and validation environment. And the CCMC, I think, is working toward that with their AWS cloud resources. Open source distribution and reproducible deployment using container technology and using what's called continuous integration and delivery pipelines. And basically what that means is that you accelerate the process of when you make a change to your repository. Unit tests are done, validation tests are done, and that becomes available for people to use or to take and just further develop. And also, I just want to say we're hiring. We have stable funding for 4 years thanks to LWS Strategic Capabilities Program. So any of you who are interested in model development and interested in particular in developing new models that go beyond the traditional MHD approach, and you want to run on big computers and have fun, come talk to me or come talk to Chris Bart as well. And last but not least, when I talk about model validation, so the other half of the GEM program, in addition to these theory campaigns, is ground observations and low Earth orbit observations. And I think this is really the best way to test these models of collisionless reconnection and how they couple globally to the ionosphere, because you can really get at some of these kinetic effects that I just mentioned. So for example, how does the reconnection electric field map to the ionosphere? What is the impact of Hall fields on the ionospheric convection? Maybe we can see some of that with SuperDARM if we know what we're looking for. How do these reconnection generated field-aligned currents propagate to the ionosphere? In particular, the Hall fields that I was talking about. Maybe we can see some of that with Ampere if we know what we're looking for. And how are reconnection generated particles transported to the ionosphere? So what is the impact of this non-local transport and collisional interaction, wave particle interactions, all that stuff? What impact does that have at low altitude? And there are missions coming up like tracers and GDC that are really going to help us get at those questions, because they're going to be very high time resolution observations. And so here's my potpourri of observations that we would like to have that can test some of these this new generation of kinetic models. SuperDARM, Bea Gallardo-Lacourt has done really nice work trying to relate auroral streamers seen in Themis ASI to SuperDARM images, SuperDARM observations of convection. And the thing that I really love about this is that you can actually see that the relationship between the auroral streamer and the fast flow kind of changes as the thing propagates in. There's this displacement, which may be consistent with some of the MHD pictures of field-aligned current generation by flow breaking in the intermagnetosphere. So it's really nice that you can see some of this stuff in the radar data in the ASI. Also with Ampere, you can see structures in the field-aligned current system that can't be explained by MHD. Natasha Buzlikova has suggested maybe this might be a signature of Hall effects that are not modeled in the MHD picture. Christine Gabriels has really produced these beautiful pictures of mesoscale structures in the ionospheric conductances. And I can't go into the details of this paper because I don't fully understand all of it, but I love these pictures. And I think this is going to really be a nice way of validating some of these models, right? If you have electrons precipitating in from a fully kinetic model from the magnetosphere, what impact do those have on the ionospheric conductances? And then finally, tracers, right? So we're going to observe at low altitude. We're going to have 2 spacecraft in low Earth orbit, a sun synchronous orbit. and they're going to have very high time resolution particle observations. And they're going to be kind of comparable to MMS, but at low altitude. And if you look at, for example, DMSP, which had, I think it was 2-second resolution, I don't remember off the top of my head, you can nicely see these ion dispersion structures, and this the same time of flight effects that Onsager was talking about in the plasma sheet boundary layer. He also did some modeling of the day side. You can see these nicely, but you can't see the electron edge of that. We just don't have the resolution. So tracers is actually going to have the resolution, 10 to 100 times faster than this to really resolve the decoupling of the electrons and the ions at the separatrix boundary. So that's very exciting. And so the path ahead, I think, is really exciting. We have all of these different approaches people are exploring. We have Hall MHD, we have this multi-moment hybrid codes that are now very sophisticated and can do large magnetospheres. The Vlasiator code, which is a Vlasov version of the hybrid code, where you solve the Vlasov equation for the ions. We have now Hall MHD with embedded PIC simulation, which is kind of an amazing technology to have. So you can get actually finite Larmor radius effects from this. We have these two new Living to the Stars strategic capabilities projects, Delzano et al., which are developing, I think, in collaboration with the Gamera code, which is going to be a Hall MHD with embedded spectral plasma solver. So I just looked at this paper, and that's very exciting to me, to be able to solve the Vlasov equation using a spectral approach. And then we have what I just described, this collisionless Hall MHD model, which we call MARBLE, that's also under development. It's not yet clear which of these will emerge as sort of the approach. I don't think there has to be one model. I think there can be an ecosystem of models to choose from. But what I do know is things are going to get pretty exciting. We're going to be able to explore all these crazy new ideas. That people are also exploring machine learning approaches for doing some of this modeling, building a surrogate model using a machine learning approach to accelerate some of the computationally intensive parts of the code. We're going to learn new things about how plasmas work in these large systems. That's not something that's accessible to the laboratory. So the magnetosphere is really the only, one of the few places where we can actually do in situ observations and see how these things work in a very large system. And we're going to gain new insights about old problems in magnetospheric physics. And so very exciting times ahead. I'll leave you with a much more eloquent version of what I just showed on the previous slide. And I'll just leave it at that. Thank you.
So let us thank our speaker, Dr. Dorelli. And now is time for questions. Alex.
Thanks, John, for a very nice talk. One question I have is some of these MI coupling.
Please make sure that all of the questions are on microphone so that the remote participants can hear them.
Got it. Thank you. So I was just going to say that, some of the MI coupling and, time of flight effects you talked about, you mentioned upcoming validation with tracers and GDC to really help validate the implementation of these codes because of the fast time resolution. But I'm wondering actually if another part of that could also be measurement of the upward going electrons. So you don't just see what's precipitating, but what's coming back up. And I think that's planned for GDC. And so I was wondering if you agree with that.
I do fully agree with that. I think you need to get the full, both directions to calculate things like pressure anisotropies and those sorts of things that are going to be predicted by the models. And I know GDC is going to do that. Tracers is not going to do that because it's focused on the precipitating stuff and trying to resolve the electron edge. But with the combination of those two things at high time resolution, I think we're going to learn a lot. But you're right. Yeah.
All right.
Thank you, John, for wonderful talk. So you mentioned about some MI coupling and how this kinetic physics would impact the MI coupling. So I know that there is a multiple approaches currently available, like a whole MHD, some patchwork on the dayside metapause, and make that whole physics ongoing, and then do the whole global simulation. So I'm just curious if we're using the whole MHD, then did you see any difference in the ionosphere coupling? So for example, field of line current is actually changed if you are using whole physics. That's one of the things that I'm really interested in as a MI coupling scientist.
Yeah, so that's a very good question. And we have not done that simulation. We have not implemented any ionospheric electrodynamics in the Hall simulations yet. And I don't think there's a code yet that does that properly. Oh, go ahead. But
Yes.
I can stand corrected if necessary.
Yes, but you have your MHD model would stop in the inner boundary. Have you seen the inner boundary condition and how it looks different compared to the others?
We definitely do see that. Yeah, so like I showed with the Ganymede simulations, you do see that this Hall pattern does have a global extent all along the magnetic separatrix and goes all the way to the ionosphere. So that's why, that's what motivated us to wonder what impact does that have on the usual MI coupling approach, where you map field of line currents down and use those to calculate ionospheric conductances. Once you realize that Hall physics goes there, then you have to worry about how that impacts the ionospheric conductance as well. It opens up a whole sort of can of worms there that you need to address. Yeah.
Thanks for explaining to me what Russell Kohlrausch was doing in 1983 when I was a grad student there. I had no idea. Number one, well, I was there, and it seemed in my graduate days, we spent a lot of time at the PPL Fusion program deriving systems of equations to various levels of approximation and never solving any of them. I guess part of that was, lack of computing power. But all I came away with was confusion about which is quote unquote the right level of description. So I guess my question is, assuming this program goes forward successfully and one or more of these computational approaches gives new and more accurate results, how optimistic are you that those can be boiled down to something that can be kind of feel like a subgrid model, sort of a concept that can be incorporated a little artificially in simpler, not enormous scale simulations?
Yeah, so that's a good question. That's what motivated us to go down this path of drift kinetics. We've been thinking for a long time as a modeling community, how do we parameterize these effects into large scale simulations as some sort of transport coefficients? But when you start doing the Hall simulations, even a simple model like that, you realize that you have these global effects on the structure. The whole field of line current pattern then changes and can have significant implications for understanding auroral substorms and just everything going on. That's how the magnetosphere is driving the ionosphere. And the way I got led to drift kinetics was by reviewing the literature on plasma sheet boundary layer and these particle approaches and they knew nothing about Kohlrausch or any of that complicated drift kinetics, gyrokinetic stuff. That was just, let's just apply Liouville's theorem with E cross B drift and parallel and get these amazing pictures of the distribution functions. You can observe them. So they're there. You have connection with observations. And so then in going back through the literature, you realize that some of these early models, drift kinetic models, really capture both of those things, the Hall generated currents and the particle transport. And it's sort of the way I think about it is the minimal physics model. What is the minimal physics that you need to capture those effects? And I think that's what it is. So I don't think subgrid models are really going to work here. I think the MHD spine needs to at least be a Hall MHD spine. And there's some hope that we can do that with computing resources that we have now, or maybe 5 years from now. It's much less computationally expensive than a global hybrid code. And it has some really interesting physics that we can make direct contact with observations. So that's my answer to that. I don't think subgrid models are really going to cut it, at least for those effects, the dispersive Alfvén waves, the parallel currents, those kinds of things. But we do have a drastically reduced model that can model those effects. And then when you start talking about FLR effects, like at the reconnection site, the Spicer orbits, for example, there you have some hope that you might be able to parameterize that because it's so spatially localized. It's not extending over the global scale.
Coefficient for the adiabatic invariant that gets broken. Sorry, something like describing the micro breaking of an adiabatic invariant at the
Yeah, right,
associated with
exactly,
Spicer.
exactly. And then maybe we have to go with a full hybrid code way down the line to do the ions, because like I said, the magnetosheath and the bow shock and all that stuff, there's no hope of doing that with drift kinetics. You really need a full hybrid, you know, model to get those effects.
So we're never going to.
But for the electrons, I think we can get away with drift kinetics plus some clever parameterization of the violation of frozen flux.
We're never going to get back to doing a magnetosphere simulation on a PC, it sounds like.
No, not unless it's connected to the cloud and you have bazillions of GPUs.
Any questions?
Okay, the last one.
First, thanks, John, for a really outstanding talk. And I wanted to emphasize 2 points you made at the very end of your talk. One was you told me that the models you're developing, you're putting in containers. And that is critically important. If we're ever to reach the goals of the FAIR initiative of making things transportable and multiply usable. And I think it's commendable for anybody to do that because it's the only way it's going to become really transportable, that and putting it into something like GitHub. The other point you made at the very end, that great list of all the different types of simulations models that have been developed. And I think it's important to remember that there's a whole range that goes from single fluid MHD all the way up to PIC. And you pick your tool of the problem you want to solve. All of it have applicability, but you got to be careful. You want the one that's applicable to your particular problem. Thank you.
Yeah, thanks. I agree.
Thank you. So now I would like to invite Dominic Slumpa and Ravinder Goyal to introduce Mike Liemohn.
I'm just doing the intro. Okay. Hello, our next speaker is Professor Mike Liemohn. Professor Liemohn's research interests focus on plasma transport in the ionosphere and magnetosphere of the Earth and other solar system bodies. Professor Liemohn received his PhD in atmospheric and space sciences from the University of Michigan at Ann Arbor, and then he had a postdoc position at NASA Marshall Space Flight Center before returning and ultimately becoming a professor in the same department. Mike is also currently the Space Institute Director for the University of Michigan, and the title for his talk today is The Hidden Gems of Intermagnetospheric Research. Please help me welcome Professor Mike Liemohn.
All right, so first test is see if I can tackle the technology. Hey, so far so good. Do I need to do any screen sharing thing? We're all good. I see thumbs up. Okay. All right. So welcome to GEM. Happy Pride Month. Happy belated June 13th or Juneteenth, which was yesterday, but today's the holiday, official holiday. So happy Juneteenth and happy belated Father's Day to all the fathers out there. I'm thankful that we're all here in person for our first GEM in a few years. GEM is a great meeting. I hope that you enjoy your week. Stay safe out there. I'd like to start with my acknowledgements just to make sure that I get them in. And up here, you'll notice that I have a land acknowledgement. And this is so that we know our past and know that colonialism and imperialism have repercussions today. And not that we can change our past, but knowing that past will help us to strive towards a better future. So when I was asked this, I was wondering what topic should I pick for my for this tutorial. I went around, I was searching through the literature, I was reading a bunch of papers, and finally I reread the email and it had this text in there, and I read the first half of that as saying, say something about the inner magnetosphere. So I will. But I read the second half of that as, feel free to riff on whatever topic you want. So I will. So I made this a little bit different than perhaps some others have done here. Instead of taking the focus on one topic and looking at it from several different aspects, I took it as looking at many topics from a particular angle. And so the particular angle that I'm looking at are hidden gems. So today we're going to talk about hidden gems. So what do I mean by hidden gems? This is something that is very high quality, but has not yet received much attention. So we can define that in many different ways. What does it mean by high quality? What does it mean by lots of attention? We'll start off with a definition of peer-reviewed literature. And so with that, what do I mean? Space physics. I've done a little bit of investigation of this. We have very few papers with 0 citations. If you look out maybe 10 years past, and certainly further back, the number of papers with 0 citations drops below 1%. And that's really good, because there are some fields out there where it's 50%. Yeah, that mouth right there. Yeah, so we only have 1%, you know, that's fantastic. We have very few lost papers out there, but we do have quite a few with you know, not too many citations. And so those are the ones where I took a look at these papers as I was going through this big literature search of what I want to talk about, and realized that there are some really good papers out there that don't have a lot of citations. And so, okay, I'm going to highlight some of them. I'm going to tell you about some of my some favorites of mine over the last 10 years. And I specifically focused on, well, maybe I should really make this 2.5 to 10 years old papers with less than 10 citations. So they had to still be in the single digits. And I did a search with a bunch of keywords in there, and also, you know, other papers that I was finding. And so it's a smattering of topics, but I'm going to keep it on the inner magnetosphere, at least here at the beginning, and then I'm going to drift a little. And so sorry if I didn't include yours. I only have so much time up here, and well, we'll get to that in the end. So I'm going to start with the ring current because of the 3 major charged particle populations: ring current, plasma sphere, radiation belts. Ring current is where I've spent most of my time, and so I'll start there. And I'm going to start with this paper. We, the collective we of humanity, but specifically Conoco and co-authors here, have discovered molecular ions in the ring current. Molecular, not just O+ and N+, but O2+ and so on. And so these particles presumably made it out of the high latitude ionosphere, out through the lobes, into the plasma sheet, hit the plasma sheet, were re-accelerated back in, and are now 50 keV. And they don't see them all the time, but they do see them some of the time. And it's not a high percentage, but this one right here on the cool factor, I want you all to know about. We've discovered molecular ions in the magnetosphere, singly charged molecular ions that came from our upper atmosphere. So there's that. This paper, superposed epoch analysis. So I love a good superposed epoch analysis. Figure out, if you don't know that technique, please learn it. So what is this? This is when you choose a particular reference time and you align events according to that time. So this was aligning events based on DST minimum, and then looking at many different drivers and many different geomagnetic index responses to it. And not only doing it off that, but also dividing it up by universal time. And what do you notice here? The red curve is different. That the local time, the universal time of you know, plus or minus a few of 2 UT has a slightly different curve than all the others. And so when is that? 2 UT. That's when the Atlantic is the Atlantic sector is near midnight at storm peak. So during the development of the storm, and if you look at AL, it's not just it's not just DST or SIMH as it is here, but also AL 12 hours earlier. So when the US sector is over on the day side, we have extra strong substorm activity as well. So it's easier to see the aurora in, say, Moscow than it is Ann Arbor. We should move there instead. Okay, moving on. Steady magnetospheric convection. This is, I like modes of magnetospheric processes, and I think that we do have, there are some states of our geospace system that it gets into a particular process, processes dominate and it gets going in a particular mode for a while. One of those we've deemed steady magnetospheric convection, and what I'd like to show you here is that the ring current plays a role in that, and that it isn't just an external driving level that you need in order to get into steady magnetospheric convection, but you need some internal energy buildup and development, and that the presence of a ring current, a small ring current, not necessarily a large one, a small ring current will help to stabilize the magnetosphere and get you into that steady magnetospheric convection process. So what we're looking at here on this chart here is the gray circle on there is the region where most of the data are for typical times of IMFBZ and SIMH, and the pink curve there is the region with most of the points for SMCs, and the two are shifted from each other, but not by much, just a little bit. So you need a little bit of ring current in order to stabilize it for SMCs. I found that to be an interesting result and a nice way to go about doing it. So congratulations to them. Is Miles in the room? Yeah. Anyway, so this paper here, three big things I like about this paper. One, it has a really nice table of all the updates that they did for the RAM SCB code. This is the new standard reference for this code. Really nice demonstration of how much work they have done for updating that code. Another one is this plot, and many others like it, and it's the purple-orange color scale. It's a colorblind friendly color scale. I'd like for us to get away from rainbow. 1 in 8 men are red-green colorblind. Yeah, there are many of you out there probably. I'm not going, don't raise your hand. But you know, we're in Hawaii. You can get away with a rainbow color scale here for this week. But once you go home from here, please start to think about replacing that rainbow color scale, because green is not accessible. It is not inclusive. It's better to start switching away from that. So congratulations on using a colorblind friendly color scale here. And the last thing that I really like about this is the robust use of data model comparison metrics. Some of you might know I'm on a little kick about that right now. And they used several different accuracy metrics, several different bias metrics, 2 different skill scores. They made up a skill score based on MAE. Fantastic. Way to go. Good work on this one. Switching now to the plasmasphere. I like this paper because this paper is one of those that it's not the heat, it's the humidity. And what do I mean by that? I mean that this is a data analysis paper looking at a satellite that's flying in the near Earth region, and when it would pass through eclipse, sometimes they would see the temperature plunge of the plasmasphere. And you're like, huh, okay. But then other times they wouldn't. And so they have this great, picture 2 side by side, one of them with a high temperature during eclipse and another one with a low temperature during eclipse. And they're like, okay, what's causing this? And so they looked at it. It's not where the spacecraft is, it's where the ionospheric footpoints of the spacecraft's magnetic field line are. And so this chart here that you're looking at are the solar zenith angle of the 2 footpoints. And that when both footpoints are in eclipse over here, that's the time when you get the cold the cold plasmaspheres typically. And so I like this. It shows that you need that ionospheric heating and that production of atmospheric photoelectrons, which then go up the field line and can collide with the particles and the heat heating from the down in the ionosphere and the heat conduction of that. And I'm a sucker for a good atmospheric photoelectron paper too, since that was the field at the start of my career. Heiligen Lure. This is one that is combining two spacecraft sets. So what I really would like for us to start doing more of, and we've been having conversations about this, are more multi-satellite, multi-constellation data analysis projects. And so this is one where they use Swarm, that's a low altitude spacecraft, and they, from the Swarm data, they produce this small scale field line current index. On its night side pass, it's the latitude at which they start to see the field line currents, the strong fluctuations of the field line currents. And then they use Van Allen probes to say where the plasma pause is. And when it's on the night side, those two are highly correlated. They're right up next to each other, and the typical position is that the plasma pause is inside of the field line current fluctuations. So those are not overlapping. On the day side, they notice this correlation continues, but there's a big time lag for it. And so, it basically goes with co-rotation. So this is one where they used multiple spacecraft constellations and to understand this physical linkage between these two. I like it. Nukakar's paper on plasmaspheric reconstruction. So, we have TEC from GPS satellites. We can do that. We have lots of ground-based GPS receivers from which we can get TEC. But total electron content is dominated by the ionosphere. And so in order to get the plasmasphere, the high altitude part of it, you have to make sure you aren't looking at the ionosphere. And so you can do this from low Earth orbit. If a LEO satellite has a GPS receiver on it, then you can look at that the content above the spacecraft, which is in the plasmasphere. And so that's what they did here. But we only have a few of those satellites, and so it's spotty and it's hard to get a good reconstruction. And so others have done this before, but I like this paper because of this extra thing of the new technique that they did for the roughness penalty in order to smooth out the results and get a more realistic reconstructed plasmasphere out of it. We have TEC all the time from the GPS spacecraft, and we now have enough low Earth orbit satellites with these GPS receivers. We could do this a lot more, and we can and should be using these reconstructions as our plasmasphere. So we wanted to make that paper aware to people out there. Moving on to the radiation belts. Greg, you in the audience? Yeah, right there. Okay, so this is a hefty paper to read. Yeah, there are a few equations in there, but there are also some plots. And so what I'd like to say is that radial diffusion isn't dead yet, so local acceleration definitely does matter, and we just had a whole spacecraft mission there, the Van Allen probes that really investigated that and showed us just how important local acceleration is. But radial diffusion, we often were taking the DLLs and so on from dipole magnetic field lines approximations from it. This really showed that, okay, even during the way inner magnetosphere in this inside part right here, even this is tens of % higher than 1 on this ratio between non-dipolar and dipolar fields. And out near geosynchronous in this outer part, this is a factor of several, in fact, a factor of an order of magnitude higher when you have a non-dipolar field instead of a dipolar field. So the story isn't done yet. We still have more work to do here. So congrats, Greg, on that one. Another paper that I'd like to mention is this one by Alexa and company. This is a space weather applications one. And so as we do research here, way down here at AUL1, that's what mostly we're going to talk about here this week. But as if you're one that we fly a lot of spacecraft in the inner magnetosphere, and it's where society relies on those spacecraft. And so we can and should be thinking about transitioning our research codes into operational usage and using these codes for decision making. And in order to do that, in order to reach that state where you can look at a model output and say yes or no on some operational decision, you need to test that model a lot. You need to do a lot of metrics comparisons on it, and not just any comparison, but specific to your particular usage. And so this AUL process is laying out the structure of how you would go about it. And this middle section here, these three right here are all about validation of ramping up the scale of data model comparison to get more and more towards your specific usage, and knowing the strengths and limitations of your particular model, so that when you get to phases 7, 8, and 9, and you're up to trying to make decisions, you have a firm foundation on which you can trust what the model output, or when you can say, yeah, okay, maybe I'll make my decision on this over here instead of that. And so this is a process that walks you through it, and I encourage you to go back and read this paper along this that describes this technique of going from basic research to operational usage of a tool. So I'm going to pause right there just for a second and take a step back and say, why are some papers get lots of citations or not? And in terms of great, I don't know. We need to read more literature, I guess. So I encourage you all to go out there and we don't have internet connection in here, so sorry. You can't do it now. Don't do it now anyway. I'm talking. Yeah, we're here. But what I'd like to say is that when you do have that chance, please go back and do a thorough search for additional papers on your topic and really understand the context of what your new result, how it fits in with other people. But if we remove the word great and just focus on papers in general, then we can start addressing this with a whole separate field called bibliometrics. And that's where you're using statistics to understand the impact of publications. And so I think that that's a good field that we should pay more attention to. Just, I guess, one small thing about that is that it is fraught with interpretation. That, right, Pat? A number without context can sometimes be taken out of, taken in a wrong direction. So you do need to think about the specific causal connections and what's behind it. But given that, there are some good studies of that, and I'd like to talk about a couple of them to continue my hidden gems theme here. I actually have, I don't know, a few dozen posts actually at my JGR editor's blog. I'm not writing more for that because I'm no longer the editor, but it's still up and you can go and look at it. And so I'm not going to talk about this stuff right now. I'm going to talk about a couple others that we actually published in JGR. So the first is Moldwin and Liemohn. So this paper, Mark did most of the work for this, but I helped him, and we talked a lot about it. So we looked at all the papers published a particular year, and we analyzed certain aspects about them and tried to look for what makes a paper, is there any relationship between high citations and features, attributes of those papers. And these were all about 5-year-old papers when we downloaded the citation references for it. So one of the 3 things that I'd like to point out, more authors. We can understand that. The more authors you have, the more people are aware of it right away. And so you end up with a higher discoverability about it. The other one is citing more published papers. Again, higher discoverability. People, then are doing their literature search and they see, who cited this and, and so on, and they can backtrace the citation tree and they might find this. So, okay, both of those are very understandable. Colon in the title, really? Colon in the title. So the only thing that we could guess is that it separates the title into a short, pithy, understandable, nugget at the beginning, and then the longer, more detailed thing. We did the second half of this is that we did number of words in the title, And that is not correlated with higher citations. So it's not the fact that you have the words, you know, so maybe that it is that separation of a short title at the beginning and then a longer description. I don't know. This is one where we weren't sure, but you know, after finding this, we were sure to put a colon in the title. But unfortunately, this is still under 10 citations, so it's a hidden gem. It fits my criteria. Man, yeah. Okay. I'll talk about one other one, and that was when I became editor-in-chief. I ran a little experiment on all of you. I made it my choice to have more special sections in AGR. And so I was going out and actively soliciting people to submit special section proposals to JGR, and we upped the number by tens of percent actually in terms of new papers coming into JGR in special sections compared to previous years. And so near the end of that, I asked Paige Wooden, a senior staffer in the pubs department at AGU headquarters, to help me with this. And she gathered a bunch of numbers, and the two of us looked at them, and we wrote a paper about it. And so one of the big thing I'd like to point out to you is that the blue columns are taller than the green columns for pretty much every year. And so what does this mean? Papers in special collections, as AGU likes to call them, are on average receiving more citations than papers not. So this is the year published along the x-axis, and then this is the average citations per papers in that. And so some years, yeah, it's weird. I don't know what's going on here. Bob, were you EIC at that time, or was that back in Art Richmond's day? Yeah, okay. So we need to ask Art Richmond about what happened in 2007. But in general, you see that the blue columns are higher. So special sections work. This is what I took away from this, is that, and we looked at a number of different reasons, you know, why this might be. But the takeaway point is that special sections are in general good for having people find your paper and cite it later and build on it and move forward. So I encourage you to take the extra time when there is a deadline for a special section in your field. Make the effort to write that paper for that special section and try and get a paper into it. It's worth your time. And also, I'd like to make the call to all of you, take on that extra leadership and service role of organizing a special section. And I'm looking at all you focus group leaders out there, that it's worth the effort for the community, so that the papers are, so the work that is going on here at GEM is written down and captured in the record, and hey, it'll pay off eventually. A final thing I'd like to point out about this, and that is the upward trend of all these numbers as year published gets further and further into the distance. This beginning part of it from 18 back to 12 or so is fairly linear. And then it seems to level off a little bit. The citing half-life for JGR is right about 10 years. So even though this is leveled off, it's actually not asymptoted. It's going to keep going up, and there's going to be more citations as you go further and further back until over the history of time, the average paper will receive about 50 to 60 citations. So that's a number for you a little bit of trivia for you out there. This upward trend though is about 3 per year per paper here at the beginning. And so if your paper is hitting that number, you're average. If you're above that, all right, you're above average. Speaking of above average, inner leg peeps, we win. Yeah, all of your special sections were above average. Yeah, way to go. All right, so on this note, I would like to say that I have taken on a new editorial role, and that is a guest editor role. I'm not actually an editor right now, but we will be working on the editorial process for new papers, and this is with the journal Frontiers in Astronomy and Space Sciences. And I'm doing this, Joe Borofsky, who's the new chief editor for space physics at Frontiers, asked me, and then I asked a bunch of people. So thank you, Alexa, John, Chigo, Soshit, and Mac for helping me out with this. We're all very excited about this, and I hope that you've seen some announcements about this, and they're due at the end of the summer. So, so please start thinking about putting this in. It is not your normal research topic. It is, and they call them research topics, not special collections in Frontiers. This is not about our science. This is about our community. So I'd like to say a little bit more about that. One is our community is not diverse. Here are some numbers of self-identified gender from a few years ago. AGU did a survey, and this is the magnetospheric physics section. This is us. None of those numbers look like the general public, not even the student one there. And they didn't even bother to ask the question about non-binary at the time. And there are some surveys out there that put the non-binary population at 1 to 5%. So significant minority there. So yeah, we are not hitting diversity in this, but I like that student number. It's in the right direction. And this is one of the things I love about GEM. I love that GEM has such a younger than average crowd. And this is achieved several different ways. One is that there's a lot of financial support for students to attend. The other is that we have this very broad leadership spectrum for it. We have focus groups, a number of focus groups, lots of people rotating in as leaders and research area coordinators as well. So there's a big crew of you. Many of you are in the GEM leadership or have been. So when I was GEM steering committee chair, which, oh my gosh, it's been a decade, I think, that was right at the beginning of focus groups. We used to have this other thing called campaigns and working groups, if you remember back then, for those that were around. And we made this switch from campaign that, I don't know, the structure wasn't working for us. And we said, we need to change something. And Jimmy Rader, who was the steering committee chair before me, changed it. And basically all the working groups became focus groups. And then I became the steering committee chair. And it was the first time that focus groups were going to come to an end. And people were like, really? Yeah, and it was frustrating. It was a difficult conversation to tell people you're not going to be part of leadership anymore. And I'm sure some people were frustrated with that, but I think it's worked out in the end. A lot of people have been able to rotate through serving as GEM leadership. And I hope that we avoid burnout that way by having it constantly churning and mixing. And so I encourage the younger people out there to pay attention this week and think about those focus group possibilities coming up and leadership roles within GEM. They will be available to you. So, and I'm also very proud of the GEM leadership, the way that they've taken on the hard task of policy changes towards making GEM a more equitable experience for everyone. And we saw the big list up here. Thank you, Vanya and all the other leaders of GEM over the years that have pushed for that. So a final thing I'd like to say about this, well, not final, I still have a couple more slides. This special issue, we are not sociologists. We are space physicists. So this is a special issue by space physicists for space physicists. And so I encourage people to write about their experiences, about committees they've served on, actions they've done. Yeah, I'm looking at Vanya and Adam Kellerman about writing something about what's gone on with the GEM experience here along the way, and that could actually be several papers if you wanted to each write about your own experiences with that. And what do I mean by that? Frontiers has some different types of papers, some different paper types, I should say, to word it that way. Not just research articles. In fact, we're not expecting many, if any, research articles. We're expecting opinions and perspectives, and maybe some reviews. And these opinions and perspectives are short. A GRL has a publication unit limit of 12, and that's 500 words or one figure or one table. So if you look at that, the opinions up here are only 5 pub units long. Perspectives are 8 tops. And so these are not long papers that you can write. You do have to add in citations. You do have to think about how you've been the buildup of this particular topic, and you do have to make it relevant to the space physics community. So there are some standards for being in a Frontiers journal, but you can make it a personal perspective, and you can make it fairly short on this. So I encourage you to think about writing one of these papers for that. And by the way, if you're at TESS, anyone going to TESS, we will have an oral and poster session with exactly the same topic, and about I don't know, 10 or so in each of those sessions on Monday and Tuesday of the TESS meeting. So I'd like to tell you about the paper that I'm going to write for it. And so one is, I'd like to say, it is mostly from my JGR blog. I'm going to try and summarize that, but I'm going to summarize it here for you right now. Active DEI should be done by all. This is not something that should focus on those within certain groups. It should be done by everybody. We should all be feminists. We should all be anti-racists. We should all be allies. We should all be advocates. And thank you. Okay. So I can start right now. Today, we have a special bystander intervention training this afternoon. I've gone through it before. Many of you probably have gone through it before. Do it again. Practice makes perfect. So there's this book by Daniel Kahneman called Thinking Fast and Slow. It's a monster book. You probably don't need to read it. Let me summarize a quick thing here. So we have a fast brain and a slow brain processes that go on. Our slow brain is our thinking brain, where we're actually deliberating things and making decisions that way. The fast brain are the automatic responses that our brain has. We can train our fast brain by spending more time on it with our slow brain. And so the more we think about it, and the more we have, getting the ideas down in our slow brain, our fast brain will eventually change, and that will become our automatic response. So I encourage you to go through bystander intervention training yet again if you've done it. And if you haven't, start. Today's a great day. We're offering it, everybody. So please be here for that session. We need to get into that practice that, how does Megan Rapinoe make so many goals? It's not because, hey, you've done it once and I know how to shoot from the spot. It's that she's done that many times in order to make that. To put a DEI spin on it, we know the name Rosa Parks. She's a hero of the civil rights movement. But let me tell you that she was prepared to be that hero that day. She trained to be able to sit there and have that scary confrontation on that Montgomery bus. That was not a one-off thing for her where she decided that morning, I'm going to go do it. She'd been thinking it for months and had been actively working with other people to be able to be able to do that. She had got it into her fast brain by the time she was there. So that's something that all of us can take on. Another thing, easy. Well, maybe not easy. We need to train our brain. Singular they. If you don't know how to use it, it's very simple. It's exactly like you. You are, when I'm talking to Raluca here and I say, you are a space physicist. I used are instead of is, because even though I'm only talking to one person, it's a plural, but I'm using it in the singular. That's what we mean when we say singular they. You say, so if Raluca and I are talking about Vanya, they are a space physicist. It's that easy. We can do it. We can learn this. Another thing is to stamp out bro culture, especially harassment at that level, but also the insidious little comments that we make. That so many things are built into the way that we talk that are male dominated, and toxic masculinity is definitely a pandemic that we're experiencing right now across the world, in addition to the coronavirus. But we can deal with this right now, and so watch for these things. We'll make mistakes. And I'll get to mistakes in just a second. But so be gentle with each other when you make mistakes. But we can get better. We can do better at this. And so watch for those things and try to pull it back on yourself, and use the bystander intervention training today to gently correct somebody when they say something that that may not go along with an inclusive environment. And so I just like to say, slow down and take time to think, reword, rewrite things towards equity. To take a look around. The people around you are magnetospheric physicists. We're not famous, but we're all high quality. So I think we all fit that hidden gem mentality on that. So on that note of looking around and taking care, I'd say by doing so, this is my little flow chart of what is the scientific method. And what I'd like to point out about this are the red arrows that point upward. These are times when we're doing science and we're moving along and we realize we're using the wrong equation set. We're solving the wrong model, and we're like, oh shoot, I have to start over. And you go through and what you thought was the right thing to do turns out to not be, and you have to go back up and do it again. We're wrong a lot. And if you're doing science and you're really actively doing it, yeah, you're going to be wrong. I'm wrong a lot. And not only that, but we can get to publish at the end and of this list, and then somebody else will come along and say, yeah, actually, that was wrong. And that's okay. Our society, our community is moving towards better understanding when we have that. So I'd like to say that this can get to us. I just like to point out that imposter syndrome is real, and it can be frustrating to sit there and say, yeah, I was wrong again. So what I'd like for us to do is well, first of all, I'd just like to say you're not alone, and that you shouldn't have to go through that alone. So look for help, seek out help, people you trust, talk to them. If you're experiencing this, others have too. Many others have too. But I'd also like to say that maybe we should embrace optimism a little more and incorporate wrongness as part of our optimism. I'm an optimist. I think that hope will win in the end. And as one of my favorite authors, Sarah Bessey, she's a Canadian over there. I'm pointing at my doppelganger in the front row, Eric Donovan. Hope has wrinkles on her face and silver in her hair, meaning that hope isn't just a one-off, cheerleading session, but hope is being there every day and working through it. And Brene Brown, another one of my favorite authors, saying that you need a strong back, you need to have the courage to be brave in the wilderness, but have a soft front so that you're compassionate to others and gentle with others. So I think it's necessary for us to embrace the difficulty of our jobs. This fact that we're wrong a lot, and I think that can actually take on one of the third pandemics that's sweeping the world right now, anti-intellectualism. So being wrong, we're wrong a lot. And if we hide how we're being wrong, if it's all about being right all the time, then we're going to look at it. And when you are wrong, and sure enough, you will be wrong many times, you'll think of it as this extreme failure. And you're like one and done. Well, clearly I'm not good at this, and you'll walk away. But if we embrace it, if we're open about being wrong, and we talk more, and this is a great thing about GEM, the discussion format of GEM, of getting up and saying, I don't understand this plot. How about you? Can you help me? That's a great thing about this conference here that we're at right now. I think that when we embrace the upward arrows in this chart, that we can make science more accessible and more inclusive. So at the end here, this is my last slide, and I just like to not have a summary, but have a benediction for you. And so I'd like to say, go out into the world and discover and embrace the hidden gems, whether those be people or papers out there. I'd say go out into the world and read the friggin' literature. There are lots of good papers out there, and there's way more than you can possibly read, but at least spend a little bit of time. Don't look at that big mountain and say, I can't do it, and just walk away. Please read some of the papers. They're great papers out there. Go out into the world and set deadlines for yourself. because deadlines actually get things done. At least they do for me, and I hope they do for you too. And it's worth the effort because, like I just showed, go out into the world and embrace diversity, practice inclusivity, and work toward equity. And that can start today with the bystander intervention, and it can start later if you go home and write a paper for our special section. And finally, go out into the world and admit and embrace uncertainty, because it's in your job description and we're going to feel it. Thanks.
Thanks for this talk, Professor Liemohn. Time for your questions.
So I had a question regarding citations, which I feel a little silly now because you made those great points afterwards, great and inspiring. But I wanted to ask a really nitpicky question on the special sections. So did you by any chance look into how many of those citations from the special sections were from the people who were who published in the special sections as well? Because I often think that special sections are really useful for knowing who else is publishing in that special section. But I'm wondering, does it reach outside of that network?
Yes. Yeah. So we did do a little bit of that and trying to see the citations of other authors within the same special section. The citations within the special section of each other is actually pretty low and doesn't contribute very much to the overall citation increase. And prefaces, by the way, don't have essentially any effect on there, because in 2012, AGU stopped the process, the practice of having a preface that cites all the papers. And that was a standard thing to do. And then every paper in a special section got, +1 on their citations. We didn't do that at all during my time as editor-in-chief. So, but yes, there is some definite bonus of being in the special issue and others being able to see, oh yeah, I published here, and they go and look and see what else was there. So my guess is that is a plus up. I don't know if I don't think we did a look of people citing in the special issue later back to that. That would, I think, is really your question, and I'm sorry I didn't do that. Yeah, that's a good question.
How dare you? But thank you very much. I appreciate it.
Mike, thank you very much. It was very interesting, very insightful. I have one quick question and one probably not that quick. First, you mentioned that we have zero amount of papers with 0 citations. My quick question, did you down select self-citations?
No.
Okay, fair enough.
Yeah, so self-citations are included in that, and yeah, that can add to our having so small of papers with 0 citations that we go back and cite our own work. You're right.
Yeah, my next question is about your experience and your opinion as an editor about anonymous reviews. Do you think it's good practice, or we probably should be more open with that, open our identity, especially if we write negative reviews? What's your opinion on that?
I am in favor of dual anonymous. I think that's the future of that. Yeah. Yeah, I think opening it up, it puts a lot of pressure on young people to not say bad things about senior people when it is not anonymous. And so I think that can lead to its own problems. When it's dual anonymous, it's hard for the author to truly be anonymous. We're getting there with some of our NASA and NSF programs that are switching to DAPR, as it's called, dual anonymous peer review. And I hope that more journals adopt that process as well, because I do think it will help. So that would be my answer to it.
next?
Yeah.
So, Mike, firstly, thank you very much for a talk which was filled with many gems, both hidden and not hidden. I thought that was fantastic, and there are just too many things that I'd love to follow up on. The one question, I had two questions. The first is regarding the citation rates. It seems to me from my personal experience and speaking to others that we tend to read the papers whose authors are already highly cited. And that seems to be a problem, right? It's the Matthew effect. How do we, first question, how do we encourage people who are young and new in the field to be read more and have greater exposure? And the second question I had is, I think reading papers, the encouragement you gave is fantastic, but I think the economics are stacked against reading. In other words, it pays to write papers, it pays to write proposals. No one knows or cares if you read papers. How can we change the economics so that reading is really part of our fabric?
So yeah, you had a couple questions in there. I'm not sure. I think that's a discussion topic that we can have for this week in order to, maybe we can come up with some good ways to make it economically beneficial for people to read more papers rather than just saying, a comment up here. One is in the review process. Perhaps if the reviewers make more of a point to focus on that introduction and the context in the discussion at the other end, and say, did you think about this or that? And so in the process of accepting a review position, it might be a little more involved in the sense of you as a reviewer reading more to prompt for the author to read. But that's a service role that's asked of people, and so you have to have people say yes to that, and that's an extra burden on us. So we need to think about that and make time for reviewing as well.
Yes, thank you for the very nice talk, Mike. I have a question about this operation one, because you showed one of the slide about the Alexa study that our community kind of stuck in the basic research, not really providing the tool for the operations. In my world, I think to survive as early career scientists, we have to stay in the basic physics and get the publication out. And so more likely the operation part is kind of dumped in some area. And if we go to that direction, it's kind of a difficult route to survive in our field. So how could we change our views? And how could we say to early career scientists, yes, go for the operation and you have a successful career in the operation as well? Yeah.
I think we can redefine success as being more than just a person with many citations on their papers. I think that we should redefine success to be that you are enjoying your career post PhD, and that you, whatever direction that is, and if that direction is towards an operational focus where you aren't publishing very much, I think that we should be happy for people that make that choice and accept that. And but the other thing, I think to get a little bit to that point, we do have some journals that are towards that direction. And one of the points of here is that there's a lot of validation that goes on in data model comparisons, and those are useful, I think, for the community to know about. And so, two journals that I can think of immediately are Space Weather and Journal of Space Weather and Space Climate. We should take advantage of those two journals. The other one is Earth and Space Science, is the AGU journal, which is kind of a catch-all journal, as anything that's useful for the Earth and space science community. And that includes papers on this, perhaps not towards a new advancement or not towards a specific endpoint of operations, but the in-between steps too. So I think there are several possibilities for gaining publications on your list during this process. More funding opportunities. That's a great transition into decadal white papers. you should write one. Everyone should write one. The more that we get, the more that it will influence that decadal survey process and hopefully sway the writing of the decadal survey, and then which will eventually sway the funding agencies to put an emphasis and a priority on that. So on that note, we will have several sessions on decadal surveys on Wednesday with the MMV session. So if you see the purple MMV on the thing, want to talk decadal survey papers, the first two of those 3 sessions will be about that.
Hi, Mike. Thank you for your talk today. I think these are matters that the community must be looking at and talking about a lot more. So I have 2 things. One is first to strongly agree with the point that Jacob made about having the name of some of the authors or people on the author list count towards people's citations. I think we just have this kind of bias that there are certain people in within the community that just their name kind of puts them in a very high status as compared to other people. And I think this probably just disadvantages the early career scientists a lot. Then the second part is more of a question on the point that you raised about having a dual anonymous review process. I see it helping in terms of the quality of the papers that are being published, in that you don't know who the author is, and so you don't have that bias towards the paper itself. But then what I wanted to find out from you is, how do you see it helping in terms of the citations? Do you see it at all helping, or I don't know?
Yeah, on the first point that both you and Jacob made about discovering more papers by not the big names in the field, but by everybody else. There I go back to that thinking fast and slow issue of, when you're doing your literature search, think slowly and take your time with it, and look through the papers and not make those first judgment calls, because that's your fast brain thinking that, oh, it's a famous person, I better read that paper. So yeah, you should take a step back and go a little slower and say, I don't know this person, but it's an interesting title. You know, it has a colon. I'm sorry, no. Yeah, in terms of yeah, dual anonymous review helping citations, I think that the anonymous review does help you to be more honest in your criticism and comments about the paper, especially junior people reviewing a senior person's paper. So yeah, I hope that people spend the time to read through the introductions and discussions of papers and think more about those sections, not just the results and the new finding, but also the context in which that the paper is made. And so I just encourage everybody to spend extra time on those sections as well. Mm-hmm.
Thank you. So now we have some time for announcements for the afternoon. If some focus groups would like to tell us, leaders, what they will be talking about, or any other announcements about the sessions, and anything else you would like to advertise.
Hi, everyone. I'd like to invite you to the mesoscale dynamics in the night side transition region. We have a session here at 1:30 p.m. in the schedule, but this is a session that is joined with CEDAR. So we are going to be addressing ionospheric perspective of the night side transition region, specifically highlighting the subaraural region. Because there is an issue with the GEM CEDAR timing, the session will have a soft start, if the organizers allow me, at 1 p.m. in this room. So we will have a talk from the CEDAR side. So Phil Erickson is going to be giving an overview of the subaraural region. So we hope you can make it. Thank you.
So hi everyone. Right after this session, we're going to have IMAG CETA session. And in this session, we are going to talk about the upcoming missions, EG, tracers, and GDC. And because this is joint session with CETA, the session will go to more than 1.5 hours actually. So we start with EG and tracers for the first 30 minutes, and then we will talk about the GDC. And if you have any question about the GDC, tracers, and EG, please come and learn and ask questions, because a lot of these missions are currently in the planning and preparation status. So your opinions will be well heard. So thank you, everyone. It starts at 10:30 a.m. It will end 2 hours after that. So thank you, everyone.
Hi, everyone. We will have our magnetospheric sources of particle precipitation and its effects on the electrodynamic coupling of the magnetosphere, ionosphere, thermosphere sessions. First session this afternoon of this focus group. It will focus on observational studies today, and the standalone session tomorrow will focus on numerical studies. We hope to see you all there.
Good morning. I would like to advertise our self-consistent inner magnetospheric modeling sessions. We have 2 standalone sessions today. The first one right after this meeting, where we will discuss topics about recurrent dynamics. And the following session will be focused on wave-particle interactions, where we will start with a discussion of one of our challenge events, the May 2017 storm. And tomorrow we'll have 2 joint sessions, one of which will be with the MPEC, the new focus group. And we will have a great discussion focused on the feedback from the ionosphere to the magnetosphere. So please join us.
Okay, hello. For all the students, this is a reminder that the student dinner is tonight at 6 p.m. It's going to be over where breakfast was, and we'll have 5 panelists. So please come and hear from our panelists, and we'll hopefully see you there.
Okay, I'm going to give a quick plug for the afternoon session on speaking up. Mike already did a really good job at promoting that, but I wanted to give another enthusiastic plea for everyone in this room to please come. It's in the Bluefin at 3:30. I know there's no other concurrent session, so there's nowhere else you need to be, including on the beach. You can do that some other day and skip someone else's focus group. But today, please come to the Bluefin. We put a lot of effort into getting this group together. It's going to be great. Okay, thanks.
Thank you all. So let's have a break now.